So our lab works at the intersection of biosignal interfaces, control learning and optimization, and for health and accessibility applications for individuals with disabilities or chronic conditions. And our research leverages biosignals to develop closed-loop human AI systems that are personalized to each user's physical characteristics. Some of the techniques that we use in our Some of the techniques that we use in our lab include data-driven modeling, real-time optimization for co-adaptive human AI systems, and we do a lot of system development and evaluation. So I'll talk about some of the application areas that we're currently working on, which include home rehabilitation technologies and extended reality motor input accessibility. And something that's important to us is all throughout the engineering pipeline, we ensure that we consider our end users as well as our stakeholders through all stages of the engineering process. So we start from the beginning throughout, and we obtain intermittent input from end users throughout the engineering design, and then we make sure we do our final evaluation with end users and other stakeholders. And the big question that we would like to answer in our lab is how can we inclusively engineer novel technologies that makes healthcare more accessible? So some of the work that we're currently doing in our lab, the first one that I'll briefly talk about is developing home rehabilitation technologies for individuals with pediatric neurologic injury. So if any of you all have done rehabilitation, you know that it can be really boring, especially the ones that you do at home. And you can imagine how much more boring it might be if you are a child. And so one of the things that we're trying to do right now is to integrate home rehabilitation programs into commercially available games. Kids love to play video games. I think it's something like 80% of children play video games every single day or something like that. And in order to do this, we would like to develop personalized movement recognition algorithms that can recognize these movements that are prescribed to them for their home exercise program, as well as develop movement quality metrics. But the problem is we do not yet have a working system. So what are we going to do? What we are currently working on is this Wizard of Oz study. And so what happens in this study is we have participants who does some kind of goal-directed upper extremity movement that's related to the game. And then we have a wizard that's sitting behind the curtain, so a researcher who is watching the participant do the movement, and they're the ones pressing the right button on the keyboard or the game controller. And then that provides a video game input. So if the participant is successful, they'll receive that visual feedback. And so what does that look like in experiment? So this is a participant who experienced a pediatric stroke, and this individual is doing their prescribed rehabilitation motions. So we've got a couple of, you can see on the top left that we've got a couple of them, so like raise arm, hand flip, stuff like that. And so they're doing these motions, and they're playing a video game that I believe is called Block Soars. And so you can see that their motions are correlated to the video game. And this is not a real system yet. We are having a researcher play the actual video game, but from the participant's perspective, it feels really realistic, and it's a great way to collect some pilot data and get a feel for whether this is a system that is actually useful to our participants without putting in a ton of engineering work, actually building the system work first, and then finding out that nobody wanted the system, right? And this is the kind of data that we can get out of such a system. And so we collected a bunch of kinematic data. So you can see that we've got this participant is doing some motions, and we're able to extract their movements. And using those movements, we're able to do some gesture recognition, try to recognize their motions so that we can map them to video game inputs automatically so that they can play Minecraft using their hand motions or their whatever rehabilitation motions that they are prescribed. And we're able to get pretty good accuracy, so greater than 90%, which is really exciting. So the next work that I'll be talking about is collaborative research with Dr. Atiya Dalla from Houston Methodist, as well as a couple of other folks. And the goal here is to track prehabilitation progress at home with some kind of smartwatch. And in our case, we're using the Empatica Embrace Plus. So the idea here is that Houston Methodist has developed this really awesome prehabilitation program for individuals with end-stage kidney disease. And in order to qualify for kidney transplants, they need to have a certain amount of physical fitness in order to do the transplant. And this kind of prehabilitation protocol will help them recover faster and easier after they undergo their kidney transplant. And so you can see that they've got some resistance band exercises and some aerobic exercises. The problem is we don't know what they're doing at home, and the participants also, or the patients also, it's all self-reported. They're just tracking their own prehabilitation at home. And so how do we track it and provide some quantitative metrics? And so what we did here is one of the important things for this prehabilitation protocol is that they are doing these motions or doing these exercises at a certain exertion. And so what we did is we asked our participants, what is your perceived rate of exertion? And then we looked at how well we're able to predict that. And what we found with our 14 participants with end-stage kidney disease, as well as our older adult control participants, is that we're able to do a pretty good job of predicting these accuracies for a variety of activities, including aerobic and resistance activities. And so this is really exciting to us because this means that we should be able to track how well they are doing in their prehabilitation, monitor their prehabilitation progress, and also make personalized updates to their prehabilitation program if needed. Next, I'll briefly talk about some of the work that we're doing in virtual and augmented reality accessibility. So this is not a topic that has actually been brought up in yet, I think. More in the sense of, it's great to have patients improve their physical ability. It's great to have patients improve their physical ability and recover. However, that is not always the reality. Some people do not fully recover, and it's important to make sure that these individuals are still able to participate in work, leisure, all of these activities activities of daily living that are important for everyone. And so one of the things that we are excited about is virtual and augmented reality accessibility. Mark Zuckerberg says that it's very important that we are, virtual and augmented reality is the future of work, and I have been very grateful to Google and Meta for supporting this type of research, clearly making sure that VR and AR accessibility, VR and AR is accessible for them, is also important to them. And so we're excited to make extended reality more accessible for these participants. And so the goal of this work is to enable personalized gesture-based interfaces. Well, we would like to make this type of input more accessible. So somebody with, let's say, a spinal cord injury or stroke might not be able to do this type of pinch gesture motion. And so what are alternative ways that we can provide this type of naturalistic input? And so what we did is we collected some wearable sensor data. So this is electromyography, electrical muscle activity that you can sense from your muscles, as well as inertial measurement, so accelerometer data from our participants. And these participants have a variety of different types of motor disabilities. I believe the left two participants have muscular dystrophy and the right two participants have a spinal cord injury. And you can see that they came up with a variety of different types of motions representing different types of inputs that you might provide to a computer, such as zoom out. So you can see this upper left participant is doing a very subtle movement of the shoulders, and this is and we would like to now recognize these motions, and they're very different from person to person, as you can see. And so we developed this gesture recognizer that we actually are able to get pretty high recognition accuracy with, less than, I think it's around 5% recognition error rate with 9 training templates. And it's a very simple algorithm so that anybody can implement it in whatever user interface prototype or extended reality application that they're developing. And in conclusion, we've collaborated with a lot of people in a lot of different areas, and we're really excited and looking forward to working with you all on any of these applications, but also whatever other application that y'all are interested in. Like I said, I'm very excited to do end-to-end system development, incorporating opinions from our end users and other stakeholders. My email is momona@rice.edu. Thank you.